This is tutorial 5 and question 1. An impulse turbine fitted with a runner as shown in figure 1 has the following specifications. Figure 1 shows us a turbo wheel turbine, and this type of turbine has the jet entering the blade and exiting on the other side. The other type of impulse turbine is called a Pelton wheel turbine, and with that design we have the water exiting the blades on both sides, but we'll do another one of those problems later. Alright, I've written down all the information that is given to us. So we have a runner diameter of the actual turbo wheel of 600 millimeters. The head at the nozzle is 441.45 kilopascals. So if we convert that into a head of water, instead of pressure, we divide by 9.81 and we get 45 meters of water. We have a single nozzle. The nozzle diameter is 45 millimeters and there's a friction loss in the runner, and that is as the water flows over the blade, then the water has a friction loss over the blade as it flows over it. That is 5.9%. Mechanical efficiency is 95%. So that is as the turbine is turning, there will be friction in its bearings, etc. 5% loss there. So the bucket exit angle is 144.5 degrees. And in the diagram that I've drawn below, you can see where we measure it, 144.5 degrees. And it's in relative to the direction of movement of the blade, which is small letter u. That's the blade velocity. Alright, so beta 2, if we subtract that from 180, we get 35.5 degrees, and that is the angle beta 2. Speed ratio is a reflection of the difference in speed between the jet coming out of the nozzle and the actual blade forward direction, which is u. So that's 0.487. That is a ratio, so that's 48.7% slower than the jet. Coefficient of velocity is the velocity reduction through the nozzle. The nozzle angle alpha 1 is 22 degrees to u. Okay, so it's not in line with u, 22 degrees at an angle. And our water density is 1000 kilograms per cubic meters. So our first question is the jet velocity C1 and the mass flow rate through the turbine. So let's look at how do we calculate the jet velocity. So C1 is the coefficient of velocity times 2GHN, which is the head of the nozzle. Coefficient of velocity is 0.98. 2 times 9.81 times 45 meters is the head of water. So we can easily calculate the velocity of the jet to be 29.12 meters per second. Secondly, the mass flow rate. We put a dot above it to indicate that it's a mass flow rate and not just a mass. That is equal to C1, which is the jet velocity, times the area of the nozzle times the density of water. So that gives us 29.12 meters per second, pi over 4 times 0.045 squared, which is your area, times 1000 density of water. So our mass flow rate works out to be 46.31 kilograms per second. All right. Then we calculate our speed ratio. U over C1. That's in fact given to us, 1,487. So therefore we can work out what U is. It's 0,487 times 29,12 is equal to 14,18 meters per second. U is the blade velocity. Alright, so the second one, 1.2, is the magnitude of relative exit velocity CR2 and the velocities of whirl. CR2 and so the velocities of whirl. These are velocities in the direction of travel of the blade. Alright, to do this question we have to draw our velocity diagram. Alright, so we start off by, let's put down our U, which is the blade velocity. Right, then we've got CR1, which is the jet relative velocity at entry. Remember, this is angle beta 1. Alright, so CR1 is the velocity relative to the blade of the jet. Alright, so yeah, we've got this one would be C1, which is the absolute velocity of the jet, so that is the actual distance relative to the nozzle. This would be alpha 1, that is the angle of the blade, of the nozzle. So that's the inlet diagram. So if we draw a dotted line up here, this would be F1. It's a component, and then here would be CW1, and that is velocity of whirl, CW1. Alright, so those are all the inlet velocities related to the jet and the blade. Let's have a look at the exit velocities. I'll draw those in green. So we have CR2, which is the jet relative velocity, at exit. And then we've got C2, which is our jet exit absolute velocity. We've also got alpha 2, which is our jet exit angle, absolute angle. All right, if we look at the components, let's draw those in red. We've got CF2 and CW2. So there's your second velocity of whirl at exit. Yeah, and we also know that alpha 1 is 22 degrees and beta 2 is 35,5 degrees. Alright, so it's important that you draw all of your vector diagrams for the inlet and the exit velocities. Alright, so CW1 is C1 cos alpha is 29,12 cos of 22 degrees. CW1 will be 27 meters per second. F1 C1 sine alpha is 29,12 sine 22 degrees. That gives us F1 of 10,91 meters per second. CR1, CR1, which is the jet relative velocity at entry, is equal to the square root of CW1 minus U squared plus F1 squared. CW1 minus U. You see, that will give us that small portion of the triangle. Substituting, we've got 27 minus 14,18 squared plus 10,91 squared, and CR1 then becomes 16,8 34 meters per second. Alright, beta 1 So arc sine F over CR1 arc sine of 10,91 divided by 16,834. So beta 1 then becomes 40,4 degrees, and that's measured relative to u, which is our velocity of the blade. Alright, so now we have calculated magnitude of the relative exit velocities and the velocities of whirl. So the third question, magnitude and direction of the absolute exit velocity C2 from the runner. Okay, CR2 is equal to 1 minus 0.059 CR1. Let's do the friction loss. Which is 5.9%. Alright, so we're just reducing the inlet velocity by 5.9% to find the exit velocity. It's 1 minus 0.059 times 16,834. CR2 then is 15,84 meters per second. Alright, CW2 is equal to U minus CR2 cos of beta 2, some geometry. That'll give us 14.18 minus 15.84 cos 35.5 degrees, and CW2 then equals 1.284 meters per second. F2 is equal to CR2 sine beta 2, 15.84 sine 35.5 degrees, and F2 then equals 9.2 meters per second. If you recall from the diagram, F2 is that vertical component of C2. Alright, so now I've got the horizontal and vertical components of C2. So C2 is easy to calculate. It's CW2 squared plus F2 squared, and we square root that again. 1,284 squared plus 9,2 squared. C2 is 9,289 meters per second. Alright, the angle alpha 2 is equal to 90 minus tan of 1,284 over 9,2, and alpha 2 is equal to 82 degrees to u, u being the velocity of the blade. Alright. Then the next question is the hydraulic efficiency and shaft power of the turbine. That's number 4. The hydraulic efficiency is the power of the runner divided by the power of the nozzle. The mechanical efficiency is equal to the power of the shaft on the shaft divided by the power of the runner. Right, so power on the runner is equal to mass flow rate mg h, and this is called the Euler head. Right, so this is the Euler head, or the total head of energy in the turbine. So the power at the nozzle is a half mc1 squared. That's kinetic energy. So, therefore, the Euler head, or the total energy head in the turbine, is U, which is the blade velocity, times CW1 plus or minus CW2 divided by G. The CW1 and 2 are the velocities of whirl. So depending on the direction that you calculate them to be on your vector diagram, you either add or subtract them. So if it's the same direction, you subtract CW1 minus CW. Alright, so therefore the Euler head is 14,18 down 27 minus 1,284 over 9,81. That gives us 37,17 meters of water. Alright, so the power in the nozzle is a half mc1 squared is a half times 46,31 times 29,12 squared 19,634 kilowatts, and power in the runner mgh Euler 46,31 times 9,81 times 37,17 is 16,886 kilowatts. All right. We now know that the hydraulic efficiency is mgh Euler divided by a half mc1 squared, and we just work those out. So we've got 16,886 divided by 19,634, which gives us 86% for the hydraulic efficiency. So the power on the shaft it's the power of the runner times the mechanical efficiency. So that's 0.95 times 16,886, which gives us 16,042 kilowatts. And the final question, number 5, is the momentum torque produced by the output shaft. So torque is equal to power on the shaft divided by omega and shaft power is omega T. W is U over R, which is W is your angular velocity, as linear velocity divided by radius is 14,13 divided by 1,3. 1,6 would be the diameter. So W is in 47,267. It's actually radians per second. So if we substitute that back, torque is 16,042 over 47,267 gives us 339,39 Newton meters. And that's the end of this.